Hey guys, okay, this is the first of the quote-unquote math physics lessons. What you're going to notice is that the math in physics isn't really hard. In fact, in this, all you're going to have to do is multiply and divide. The trick to physics is that they're all what are called the dreaded word problem. You have to actually figure stuff out. And the problem with problem solving is there's two problems. One is no one ever taught you how to do it before. We've taught you how to do the math. We never teach you how to actually approach a problem. The second is it's a little stressful on your brain because you're used to on tests either having a I know it or I don't know it. With a problem, the whole point is that you aren't supposed to know it until you're just supposed to know how to get the answer. So you kind of have to shift your brain a little bit from I don't know it to okay, I know how to get the answer for this type of question. And for these, they're going to be really, really simple. So, how it works. All electric devices, so this is on electricity, which is the physics part of this course. All electric devices can be explained by the law of electric charges that we saw in the last unit. Since charged objects want to lose their charge because things that are charged, charges repel, things that are charged don't like being charged. So if you give any possible path, that object will discharge. It'll lose its charge. So the whole trick to electricity is we create a charge and we let it flow. We give it a path to flow, but because energy always can't be created or destroyed, that energy's got to go somewhere. That energy can get used up in a device that we want the energy to get to. So basically, as it goes, it gains something called kinetic energy. That kinetic energy is turned into electrical energy, which actually gives us the energy that we use to power everything that's electrical. It's literally just a controlled discharge. Now, for it to flow, you need four things. You need what we call an electric circuit. So a circuit is basically a path that is a circle so that the charge can completely discharge. By the way, there are two directions it can go in. If you do anything in electricity, you'll use conventional current. That's what we've been using for hundreds of years. If in this class we're going to use the more correct scientific one, which is the flow, following the flow of electrons, because we know the electrons are what actually move. The trouble is, by the time we discovered that the electron existed, we had been describing electricity as the flow of positive charge for 200 years. So all electricians and all electronics and stuff still talk about electricity, the current as flowing in the direction from positive to negative. We're going to talk about the slightly more scientific negative to positive. Honestly, it really doesn't change anything except the way you're drawing the arrow. So for electricity to flow, we need four things. One is a source of charge. So that'll be your battery, your outlet, solar panel, something that produces that charge imbalance. You need a complete path for it to flow from positive to negative, or from negative to positive in our case. You need something to use the energy. And in electricity, we call that a load. A load is something that uses energy. Why is that important? Well, if nothing uses the energy, in physics, it tends to get turned into heat, which causes your wires to overheat, which causes what we call a short circuit, which can actually be really, really dangerous. Unless we control, the only part of electricity that's dangerous is if we don't control where that energy goes when it's released. Fortunately, that's usually always why we're building a circuit, is to actually get that energy to something specific, which we call our load. We also need a control, a way to make this flow start or stop. Technically you don't. It's just not a good idea to make an electric circuit you can't shut off, except by, ripping the wires out, which can cause sparks. So typically we put in things like switches, which literally just break the flow so no electricity can flow. And that turns the electricity on or off for the circuit. So the current is the flow of charge. So there are a couple of words I already give you. Current, voltage, resistance. Current is the flow of charge through a circuit. So the current, think of it as the motion of the electrons as they go through. Except it's not quite. It actually goes a little faster than that because the electrons push on each other. So the current actually goes faster than any of the electrons are. So current follows the motion of the charge from the negative going up into the positive. So current, the symbol is I, The units are amperes. By the way, the symbol for charge is Q. So think of these little Qs going around and in. That's the current. So each one of these charges moves around your circuit as long as there's a whole path from the negative to the positive over and over and over and over again. Okay? I like thinking of them as little dump trucks. You'll see why in a second. I don't like the water analogy people use. It doesn't make as much sense as dump trucks. So they're the current as little dump trucks driving around a road. To measure the current, we measure it using a device called an ammeter. To work, the ammeter needs to be placed in the circuit because you're measuring how many of those little dump trucks are going by you. So if you're not here, you actually have to measure how many dump trucks go through you. Okay? So you measure how many little dump trucks go through. The red is always put closer to the positive, the black is always put closer to the negative, and that's how we measure electricity. Voltage is the most misunderstood thing because people think voltage is energy. Voltage is not the energy. Voltage is the energy each charge has as it goes through the circuit. So if your charge is a dump truck, think of voltage as being how much stuff is in the dump truck. And when you go through a source, we load the dump trucks. When we go through a load, we unload the dump trucks. But as you go around the whole circuit, you're going to see you have to actually keep the energy constant, which means if your dump truck gets loaded here, it's got to lose a little bit of its load, a little bit of its energy at each load. So the voltage is the energy each charge has. So as each charge goes through, it gains a little bit of energy, drops off a bit of energy, drops off a bit of energy, drops off a bit of energy, has no energy, gets energy, drops off a bit, drops off a bit, drops off a bit. So the energy actually depends on both how much energy each charge has, but it also depends on the current, how many charges, how fast the charges are flowing. So the faster the dump trucks are going, the more energy you're going to get as well. So voltage is not really energy in the circuit. It's the energy each charge has. You still need the current to figure out the energy. How do we measure it? Well, we measure voltage because the only way to measure it, you can't really measure energy, but I can measure how much energy something lost or gained. So the reason we talk about voltage as potential difference is when we measure the voltage across something, we measure the difference in energy it has across each. So for example, if there's one light bulb, it'll lose all its energy. If there's two light bulbs, I can measure how much of the energy is lost across each light bulb. And then that must be the amount of energy that that charge gave to each light bulb. Same thing with a battery. I can measure the difference on either side of a battery, and if each charge has 1.5 volts more energy than it did, or 1.5 joules more energy after it comes out, we know that it's gained 1.5 volts. To measure it, because we have to measure a difference, we measure it a little differently. And by the way, if you want to annoy a physics prof, especially a lab prof, to give you an idea of how much, when my old physics lab prof who I used to work for I told him that I was teaching high school, he told me he would hunt me down if any of my students ever destroyed one of his multimeters by measuring voltage incorrectly. The trick with voltage is you have to measure voltage across. So you don't put the voltmeter in, you touch it across the sides of the thing you're trying to measure. Again, the red closer to the positive, the black closer to the negative. If you put a voltmeter in, you'll blow it. If you have this set as an ammeter, when you touch it across, you'll blow it. Fortunately, we're using digital meters and electricity online, so you can't actually blow meters this class. But in the future, when you're measuring for a volt, when it's set to voltage, you want it across the circuit. When it's set to amp, current, you want it in the circuit. That's really, really important. Otherwise, you can destroy your meters very, very quickly. All right, the last thing is resistance. And when we apply voltage, it creates a push, which creates the current. However, it doesn't move without any opposition. Wires aren't perfect. So what the current does is the current is resisted by impurities in the metal. And we call that resistance. So if you think of it, pushing it through a pipe would be easy, but if we had little blockages in the pipe, you'd have to push a little harder to get it through. So that's what resistance is. That's how hard it is to push. So resistance depends mainly on the material. Something that's an insulator has very high resistance. Something that's a conductor has very low resistance. That probably makes sense, because the higher the insulator, the less the charge can move, which is why it's an insulator. The conductor, it can flow easily, so it has a very low resistance. So for example, wires have so little resistance that we usually ignore it in most circuits. We only worry about the resistance in wires if we're doing very sensitive electronics, or if we're doing something like power lines where it's going for a very long distance. Then the resistance in the wire becomes important. But in most circuits, it vanishes. So how do we measure resistance? Same way we measure voltage. You turn your multimeter to ohms, to the ohm setting, to the resistance setting, and you touch it across either side, and it will tell you what the resistance is. Now, the weird thing about resistance is the unit is called the ohm. The reason is the relationship we're going to talk about on the next slide is called Ohm's law, named after a guy named Heinz Friedrich Ohm. Physicists thought they were funny, so they gave the symbol for resistance the Greek symbol omega, which is just a little half O with some little legs. You don't need to be perfect at drawing that. You just need to remember the unit is ohms. So when we calculate the resistance, we actually calculate it experimentally. You put a known voltage through, measure the current, increase the voltage, measure the current, increase the voltage, measure the current, increase the voltage, measure the current. And you discover that you get a line with a slope of 1 over the resistance. The more voltage you put in, the more current you get, but that has a line that is equal to the resistance, well, the inverse of the resistance, actually. So, Ohm's law. Since the graph is a straight line, we can use the equation of a straight line, V, to get V equals the voltage is I times the current. Or the resistance is voltage divided by the current, by just dividing. Now, so this is the equation for Ohm's law. There's actually 3 versions of this equation I'm going to give you for those who aren't good at rearranging things. R is the resistance in ohms, V is the voltage in volts, I is the current in amps. Now, one scary thing you're going to notice as you start doing physics is there's a point to algebra. Algebra is not about doing more math. It's about only having to do the math once, and then we can sub in the numbers and get an answer without having to rearrange and do the math every single time. We simply just replace the letter with the number. So we don't usually use X for anything except position in physics. We give it, R, V, I, resistance, voltage, current. So to rearrange Ohm's law, there are 3 ways we can rearrange it. If you like the triangles, by all means, this will be on the test. If you like rearranging it like this, I'm going to put just the equations on the test as well, if we do a test. So, by the way, so resistance is voltage divided by current, voltage is resistance times current, current is voltage divided by resistance. Now the cool thing about this is if you just sub in the equation and then plug in the numbers, you don't have to think about, do I multiply, do I divide, how do I find this? You literally just write it out, plug in the numbers, and do the math that it says. If you like the triangles, the way to do that is voltage is current times resistance, current is voltage divided by, resistance is voltage divided by current. So how do we do it? Well, I'm a big fan of full solutions. Now, I have to tell you this, I did not come to this quickly. I fought this all through high school. There's a reason my marks in high school were way less than my marks in university, because I didn't like doing full solutions. I thought, I'm a smart kid, and I want to get out of this test fast. So the way I can show the teacher I'm the smartest and get out of the test the fastest is by trying to do it all in my head. Okay, I realized, A, I'm not smart enough to do it all in my head without making mistakes. In fact, I've met maybe one person in my entire life who is. Secondly, it's a lot more work, and it is actually slower because you're trying to figure it out every time on your own, instead of using the fact that the equation already has it figured out. When I started doing full solutions, my marks literally jumped by like 15%. Okay, I'm not kidding you on this. Okay, I am not some crazy person. Well, I am a crazy person, but I'm not about this. Okay, please, full solutions. The reason I'm going to pick on it is it makes your life so much easier. It's also a lot less stress because when you get a question, instead of going, oh my God, I don't know the answer, you're like, oh, this is the Ohm's law question. I know exactly what I need to do. Write down what I know, write out the equation, plug in the numbers, get an answer, give me write out a statement with units. Boom, done. Works every time. Okay? It's a lot less stressful. So let's say step one, write out what you know. So 12-volt battery, V equals 12 volts. Pushes a current of 2 amps. I equals 2 amps. Write down the units. Then the next step in problem solving is the one people always forget. Write down what I'm asking you to find. What is the resistance? R equals question mark. That may seem silly, but there's a really good reason for it. I'm going to give you the equations. If you identify what you're solving for, you know right off the bat which equation you need to write out. Write out the equation. By the way, that's worth a mark. Plug in the numbers, replace the V with 12, the I with 2. Again, that's the entire point of algebra. Now you know, divide 12 by 2, you get 6 ohms. That's the resistance. That's the right answer. Then give me a statement with a unit. By the way, one of the nice things I like about physics is it's not like a lot of courses where you can write something beautiful and think it's great, and the teacher's like, nope, don't like it. And you wonder why you got a 3 and the person beside you got a 4. Physics is nice because I can tell you exactly where the marks are coming for. You get 1 mark for this, because that shows me you understand the question. You get 1 mark for writing the equation, because that tells me you understand the physics. You get 1 mark for plugging it in, 1 mark for giving me an answer. If you forget to give me a statement or forget to give me a unit, you're going to lose a half a mark. All right, so this would be out of 4. 1, 2, 3, 4, and then you'd lose a half a mark if you didn't give me a statement or a unit, because those are important. If you don't give me a statement and a unit, this is just math. It's not actually physics. The whole point is this actually means something in the real world. This means the resistance of that circuit is 6 ohms. You could put a 6 ohm resistor into that circuit, and you will actually get 2 amps when you connect to 12 volts. If you did that in the simulation program I gave you for the level 3 right now, you would actually get an answer of 6. That's the cool thing about the physics. All right, another one. What voltage is needed to push 0.5 amps of current through a 100 ohm resistor? Again, what voltage? V equals question mark. There's my current. I equals this. 100 ohm resistor. R equals that. I know I want V, so I write this equation. V equals I times R. Plug in my I, plug in my R, get an answer. Give me a statement with a unit. That's it. It really is simple to do. Once you practice it a few times, if you do a full solution, it will always work, okay? You will always get 4 out of 4 on this question. It's one of the reasons I liked physics, is I realized physics wasn't about being brilliant, it's about being meticulous and doing it right the same way every time, okay? That being said, if you don't give me an equation, if you just write 50 volts on this, I'm giving you 0.5 out of 4. Because you didn't give me a statement, so you lost a half mark there, and you didn't give me the rest of this stuff, okay? On the other side, even if you can't get your calculator to work for some strange reason, you can still pass. Because if you write this, and you write out the equation, all of which, this is all right here, the equation is typically always also on a test, you still get 50%. Then you might as well plug in the numbers because you got them there. Well, there's 75. If you got the numbers, you might as well run a calculator. There you go. You got 100%, okay? This is, as I said, full solutions in math, on word problems, and in physics are your best friend, because literally it reduces a problem to something you know how to do. You know, if you follow the steps, you will get the answer right every time. All right. Thanks very much. That's it for me.